Welcome everyone. I am Mahdi Bahmani. In the world of cybersecurity, some ghosts stay hidden for a long time, too long. For 9 years, a silent flaw sat at the very heart of the world's most powerful operating system. It didn't care if you were running a personal laptop in Tehran, an Amazon server in Virginia, or a government mainframe in Seoul. It was there, waiting. They're calling it copy fail, discovered by Taeyang Lee and the Shincode research team. This isn't just another bug. This is a critical failure in the Linux kernel, the digital foundation of the modern world. We have seen monsters before. Dirty Cow shook the industry, Dirty Pipe terrified sysadmins, but copyfail is a different kind of beast. It is insidious, it's highly reliable, and most importantly, it's universal. With just a few lines of code, a local user with zero permissions can bypass every lock, every gate, and every guard, stepping straight into the throne room with full root access. Today, we're going inside the code, we're breaking down the exploit line by line to see how a simple copy instruction became the biggest security failure of the decade. Grab your coffee, open your terminals, let's look at the copy fail. This code is a Python implementation of a local privilege escalation (LPE) exploit. Especially it leverages a vulnerability in the Linux kernel, most likely a variant of the famous dirty py CVE-2026-31431 or a similar page cache exploit to overwrite a read-only system file USR bin su in memory. Line by line breakdown, setup and obfuscation. Imports. The script aliases OS to G and socket to S to keep the code short and slightly harder to read at a glance. Function DX, a helper function that converts a hexadecimal string into raw bytes. This is used later to inject shellcode or binary patches. The core exploit function C. This function is where the magic and the attack happens. It uses the Linux kernel's crypto API and the splice system call to bypass file permissions. AF_ALG. It opens a special socket type 38 that talks directly to the kernel's internal cryptography framework. Bind. It initializes a specific encryption algorithm, AEAD. This isn't actually to encrypt anything. It's to set up a kernel space buffer that the script can manipulate. Setsock_opt. These lines configure the crypto engine by setting specific keys and lengths. The attacker is preparing the kernel's memory to handle data in a way that triggers the vulnerability. Send MSG. This sends the malicious payload C into the kernel's crypto buffer. The payload is the small chunk of code that will overwrite the real USR bin su or su. Splice. This is the critical part. The splice system call moves data between two file descriptors, like a pipe and a file, without copying it to user space, your actual Python program. The attack. By splicing data from the crypto socket into a pipe that is also connected to the USR bin su file, the script tricks the kernel into writing the malicious data into the page cache of the read-only su binary. Loading the payload. This function opens the su binary, the program that lets you switch users. Usually you can't write to this file because it's owned by root. zlib decompress. This decompresses a compressed hex string. This string contains the binary patch. When applied to su, it typically modifies the code to skip password checking or to immediately spawn a root shell. executing the override and gaining root. The loop. It calls the C function repeatedly, patching the USR bin SU binary in the system's memory 4 bytes at a time. G system SU. Once the binary memory is patched, the script runs SU. Since the code for SU has been modified to bypass security, the system grants the user root administrator privileges without asking for a password. Now we are looking at a live demonstration of copy fail. We are starting on a standard Ubuntu installation running on unpatched kernel. Notice the first command, ID. We are logged in as a standard unprivileged user. Our UID is 1000. At this stage, we have no administrator power. We cannot read sensitive files or modify system binaries. Now, let's look at the exploit itself. This Python script is remarkably small for something so destructive. It's using the Linux kernel crypto API and the splice system call. Its goal isn't to break the door down, but to trick the kernel into letting us borrow the keys. It targets the page cache, the place where the system stores the binary for the su command in memory. Watch what happens when we execute the script and su command. The Python code runs in a fraction of a second. It has silently patched the SU binary inside the system's RAM. Normally, SU would demand a root password, but because our exploit redirected the logic flow in memory, the check is bypassed. We run ID again. Look at the result. UID equal 0 root. In less than a second, we have seized total control of the operating system. Escalation is easy. Staying safe is the real challenge. We exit the root shell and return to our normal user. Now we perform the most critical step in system administration, remediation. We run sudo apt update and sudo apt upgrade. The system fetches the latest kernel headers where the Zinc code research team's discovery has been addressed. We reboot the machine to ensure the old vulnerable kernel is cleared from the memory and replaced by patched version. Now we are running the same Python exploit on the exact same machine, but the environment has changed. We execute the script one last time. Notice the output, file not found error. The patched kernel now recognizes that an unprivileged process is trying to use a splice to write to a read-only memory page. It blocks the attempt instantly. Very simple summary. This exploit works like this. Abuses kernel cryptographic API, injects data into kernel memory, creates a small overflow 4 bytes, modifies a sensitive file in RAM, security programs don't understand, user becomes root. This is the reality of modern security. A flaw can stay hidden for 9 years, but once identified, the race between the exploit and the patch begins. In this video, we saw how a copy fail turns into a system success through timely updates. Update your operating system and kernel. Stay safe.